Hey everybody, Mr. Stone here. Let's keep talking about wave optics, the behavior of light in terms of waves. So this is Unit 4, Lesson 4, and the phenomena we're going to talk about today is thin films. What happens when we have a very thin layer, and what happens to it optically? How does it behave with light? Okay, so before we move on to that though, let's think about oh, here we go. Let's actually look at a thin film before we do that. So this is a soap bubble. So here on the left hand side you see a beautiful picture of a soap bubble, all these rainbow swirlies. On the right hand side we can actually see a soap bubble as it slowly gets thicker on the bottom and thinner on top. So the thickness of our film, that's all a soap bubble is a very thin layer of soap. It's decreasing as it goes along, and optically it's changing. It's producing this rainbow pattern for some reason. It's picking various light colors allows us to see, and something's happening at the top. It's no longer even a rainbow. It's sort of white for some reason. Something's happening up there. Some reflections happening. Not sure. Let's think about it. So what I'd like to talk about here now is index of refraction. Remember that when light hits a medium, any medium, it slows down. And it slows down by this factor n, which was the index of refraction. That is the amount by which light slows down when it hits the medium. For example, water is 1.33. So that reduces the speed of light by about 75%. So it slows it down to about 75% of what it would be in a vacuum, pretty much what it would be in air. Glass is about 1.5, so it reduces it to about 65% of the speed of light, and so on and so forth. So that's what we mean by index of refraction. Now, why do we care about index of refraction? Now, this has to do with the wavelength of the light, because when the light is traveling through the medium, it has to go up and down at the same amount. The frequency stays the same. Right? The light doesn't change color. The frequency stays the same inside the medium. So that means it's let's say the electric field is going up and down at some frequency. Now, if it slows down, right? If it's the wave here is slowing, right? That means that the wavelength is reduced. Even though I'm still moving my hand up at the same amount, because I'm moving it to left and right at a slower amount, that reduces the wavelength. Okay, so if I slow down the light by a factor of n, I reduce the wavelength as well. So let's think about this mathematically quickly. So velocity is equal to f lambda. That's our universal wave equation. And using the equation that we just saw, we saw that the v is equal to, v is equal to c over n. And that's also equal to f lambda. So if my n here increases, let's say I go to a new medium, that means my wavelength has to decrease. So my ratios of n's has to be the inverse of the ratios of lambda, because n is proportional to 1 over lambda. Right? As one goes up, the other one goes down. They're inversely proportional. So that means the ratios have to be inverses of each other. Okay? Now, what happens when light actually hits a medium? I want you to think back to grade 11 when you guys were playing with those slinkies in the halls. If you set a wave, let's say here's my slinky, and here's a person. If I set up a wave pulse down in this direction, when it reached that person who was holding it, it would reflect back in the opposite direction. This is a change in phase. This is a phase flip, a phase inversion. We flip the phase when we strike a denser medium. Now, in this case, the medium was so dense that it actually you were attempting to stop the wave, but it doesn't necessarily have to stop the wave. So let's say we have a light wave here. This is the electric field, going up and down, and it strikes this medium. The light that's reflected off of here, there's going to be a phase inversion there. I've tried to show that in the picture, but you'd imagine if it had kept going, it would be going down, but it's gone up again. So there's a phase flip happening there. Anytime that light hits a medium where the optical density, the index of refraction, is greater than the original one, the phase flips. If it hits a medium that's lower density, there's no phase change. So the light that goes through didn't change its phase. The light that was reflected changed its phase, but the light that went through kept the same phase. Now it's going to hit air again, so when it leaves, it'll have the same phase. However, the light that went through the medium, the refracted one, this is refracted here, how it changed angle here, refracted towards the normal, that's going to strike that second interface and reflect as well. Okay, so we're going to have a phase change. So there's two factors here. There's going to be a phase change at the first interface, and there's also going to be a phase change caused by the path length. However long it takes for the light to go in and out, however many wavelengths it goes in and out to go down to the bottom and then up to here, that's going to also determine a phase. Right? And that phase, if it's in phase or out of phase, determines the amount of light that is reflected off of that surface. Okay, so right now in this picture, if these are in phase, we would have light being reflected off of there. Right? If for some other reason this was slightly thinner and it changed the phase by pi, let's say, then it would be in the opposite direction, let's say the red line, then we would see no reflection. So the relative phase between these two different reflected rays decides whether or not we can see that color. Right? So let's look at some examples. If we have a very, very thin medium, okay, so incredibly thin medium, we have a thickness, call it T, that is much, much, much thinner than the wavelength. The path length difference will not cause any sort of phase change. The path difference is negligible. We're going to have a phase inversion at the first interface, but because the path length as it goes through it doesn't really change the phase, it will the second ray will be out of phase from the first one. We have a flip of phase here, but we've had no change in phase as it goes in and out. There is a slight phase change, but it really doesn't matter. Its phase change is incredibly small because it barely goes in and out. This length has to be much, much smaller. So let's imagine this thickness here is 10 to the negative 9, and this wavelength is 10 to the negative 7. Let's say it's 100 times smaller. So that'll only change the phase by 1%, right? What's that? 1%? It's 3.6 degrees, so it really wouldn't change anything, right? So the phase difference between the two rays is going to be pi, 180 degrees. They're going to be completely out of phase, and they'll cancel out. So we'll end up with destructive interference. We won't see any light. There is no reflected light off of a very thin film. Okay. Now, if the thickness of the material is a quarter of a wavelength, then the path length difference, the amount of distance that the light has to take to go down to the bottom and back up, will be double lambda over 4, so it'll be lambda over 2. Right? It has to go down lambda over 4, then it has to go back up lambda over 4, so we're going to end up with a half a wavelength shift, and that will give us a phase shift of pi, 180 degrees. So we had a phase shift happen at the interface and a phase shift happen through the path length. They're both out of phase by pi, so they're in phase again. And we're going to end up with constructive interference. There is no phase difference between the two reflected rays. Right? So we have a phase change of pi here. This up and down causes a phase change of pi. Everything is still lining up. So if the thickness is a quarter of the wavelength, then it will constructively interfere. Now, keep in mind, this is dependent on the lambda. So this might cause constructive interference for red, let's say, but that won't be the same wavelength as blue. So it may have destructive interference for blue. So we'll only see red being reflected for that certain thickness. Now also keep in mind that this doesn't just have to be pi over 4. This could be 3 pi over 4. 5 pi over 4, right? This can be any odd multiple of a quarter, right? Because let's say, let's write 3/4 lambda plus 3/4 lambda. That's going to give us 3/2 lambda, right? So that's going to be a full wavelength and then another half. So this is again going to cause a phase change of pi. So again, any of these odd multiples of quarters is going to cause constructive interference. Now if it's double that, if it's lambda over 2, we're going to end up with a phase change of 2 pi. Sorry, you can't really see that, but that's a phase shift. That says shift up there, phase shift of 2 pi, and the reflection causes a phase shift of pi. So we have our pi, we have a pi phase shift there, and then we have lambda over 2 down here, lambda over 2 down, up, down, and back up. So that's a full lambda. So that's a full shift of a wavelength over. That's a full shift of 2 pi. So in the end, the two are going to be out of phase by pi radians, or 180 degrees, and they're going to destructively interfere. Okay? So once it got, again, also, this doesn't only have to be lambda over 2, right? This could be lambda, right? It could be lambda over 3. It could be, sorry, 3 lambda over 2. Any multiple of a half, right? Because if it was, let's say, it'd be lambda down, lambda up, so that's 2 lambda. So again, we'd have a phase shift of some multiple of 2 pi, which ends up causing destructive interference because of the pi shift at the interface. So this is all about phase. Is it lining up or not? Right? If the light that reflects off the top and the light that reflects off the bottom of the interface, so these two different interfaces on this thin film, if they're out of phase, then they destructively interfere, and if they're in phase, they constructively interfere. All right? So just recap. So thin ones always destructively interfere. If it's lambda over 4, then they constructively interfere, and if it's lambda over 2, they destructively interfere as well. All right? So here, if we look at, let's check out this video here. This is a thin film in this little ring here of some soap bubble. And as we can see, gravity is going to pull it down. So it's going to thicken it as it goes down. So the thickness is changing. There's a thickness gradient as we go along it. And any time that the thickness of the thin film is some multiple of that wavelength, let's say red or blue or whatever, they're going to, anytime we see that color, that's a lambda over 4 multiple, an odd multiple of lambda over 4, because it's going to bounce in and out. Now once it keeps going thinner and thinner and thinner at the top, once we get to a certain critical threshold at the top there, we no longer see any reflection at all. We see right through it. It's completely transparent. Because at that point, all the light waves are going to always destructively interfere because it's so thin. There's no phase change due to the light bouncing off of the backside. Right? We got to keep in mind that what we're looking at in this thin film is there's a front surface that we're looking at, and there's a back surface as well. So when we see the light, there's the light that's reflecting off the front surface, there's light reflecting off the back surface, and the colors that we're seeing is the interference or the phase change between those two lights. Then there's a bunch of little water droplets or something that's happening as well that's making everything interesting. Some weird non-linear stuff happening there. But that's beautiful. You can see how here this is this incredibly thin amount at the top. Then we get here, this must be the first sort of nanoscale thickness, and then we get thicker and thicker as we go along the bottom. And in this video, we actually are observing nanoscale changes. So measurements in the order of 10 to the negative 7, 10 to the negative 8, we're actually observing that happen. We're actually seeing that this thickness of this film at the top is in the order of 10 to the negative 9. We're actually seeing a nanoscale film at the top of this ring. And there must be some sort of convection happening with the light that's shining on it that's causing all these bubbling to happen. Okay? So let's try an example here. So in the summer months, the amount of solar energy entering a house should be minimized. Window glass is made energy efficient by applying a coating that maximizes reflected light. Light in the mid-range of the visible spectrum, 568 nanometers, travels into energy efficient window glass. Now, what thickness of the added coating is needed to maximize the reflected light? This is going to be slightly different than the example we just did with a water droplet, or sorry, a soap bubble. This is going to have a thicker medium at the bottom. So there's going to be a phase change at the first surface and a phase change at the second surface. So we're going to have to be a little bit more careful here. First step, let's figure out the wavelength of light in the material. So we know that we're talking about the light inside the coating. So using lambda N2 being 1.4, we end up with about 406 nanometers as a wavelength of light traveling inside of this medium. Now, for us, we want to maximize reflected light, okay, which means we're looking for constructive interference. For the reflected light to be maximized, we're looking for a constructive interference. Now, this is going to mean lambda over 2. And now you may be saying that doesn't make sense because in the previous example you said lambda over 4 would make constructive interference. But you have to remember that there's going to be a phase change here and a phase change there. So we're going to have a pi shift there. So this one is going to be, this reflected ray is going to be out of phase from the original ray by pi. Then we're going to have a phase change here also of pi. So without any path length considerations, the two light rays are going to be in phase. Now, for us to have a path length that'll keep things in phase, we're going to have to go a full wavelength up and down. So the thickness is going to have to be a half a wavelength. So for it to go, it'll go, let's say, 1/2 the wavelength and another half of the wavelength. It looks terrible, but so we have a phase shift of 2 pi from the path length and a phase shift of pi from the phase inversion. So the two light rays that are reflected off here are going to be out of phase by 2 pi because the one has a phase change from the original of pi and the second one has a phase change from the original of 3 pi. Okay, so let's say this has a phase of 0. Let's call this, it's a phase of 0. This phase difference is going to be pi, and this phase difference is going to be 3 pi. So the total phase difference is going to be 3 pi minus pi over 2 pi. Okay? So that explains why the thickness has to be half a wavelength. So in the end, the thickness of the film has to be about 200 nanometers, or 2 times 10 to the negative 7 meters. Right? Now that's a little bit tricky. Hopefully I didn't confuse you there with that. But in the original, with the soap bubble, we didn't have a phase change on the second interface, sorry. But in this example, we have it. We're going, because this is denser again. The glass material is going to be 1.5. This is 1.5. This is 1.4, and this is about 1. So because it's going in a denser medium here, we're going to have a phase shift of pi. Here we have a phase shift of pi as well. And then for us to have constructive interference, our path length consideration has to be 2 pi. 2 pi phase, or lambda. So the thickness has to be half that since it's going in and out. All right. Okay. So here's a couple problems here, looking at some different soap bubbles and coatings, and try those. The answers are provided there. All right. So next time you look down at a a little gasoline spill and you see all those colors, just remember that you're looking at a nanoscale film. You're actually seeing the nanoscale world in that gasoline film. Okay? All right. So have fun with those, and good luck, and I'll be talking to you later.